Our last installment of notes in our reaction rates unit will be looking at catalysis or catalysts. A catalyst is a substance that makes a reaction go faster, so it speeds up the reaction rate. The catalyst itself is not used up in the reaction. It is not a reactant, it is not a product. It plays no role in the reaction other than to make the reaction go faster. It's possible that if it is used up, it may be regenerated. But the catalyst that is present in the beginning must be present in the end. For example, when we did our lab yesterday, we did the reaction with the pink cobalt chloride, and that was our catalyst. A catalyst changes three things about a reaction. It changes the mechanism and the activated complex. It changes the steps the reaction goes through and the activated complex that you make in the middle. For example, in the lab, the uncatalyzed activated complex was clear and colorless, but the catalyzed one was green. The second thing that a catalyst changes is the activation energy. It essentially lowers the barrier. It lowers the barrier of energy that the molecules need to react. In doing so, a catalyst increases the number of molecules that are able to react. If you lower the hurdle, more molecules will be able to jump over it. This increases the rate of reaction. Let's look at how this changes a potential energy diagram. Remember our exothermic potential energy diagram that we did last time. Potential energy was on the y-axis, reaction progress was on the x-axis. We had our reactants and our products. Notice that the products are lower in energy than the reactants because this is exothermic, energy out. Here's our curve. Our activated complex is always the top of the curve. This is the hurdle. This is the barrier. You have to have enough energy to get from the reactants to the activated complex before you can make the products. Here's our baseline. That's where our reactants started. And here's our activation energy. To get from here to here, this is the amount of energy that you need in order for that reaction to occur. This is our normal reaction curve. If you add a catalyst, that would change the graph in the middle only. Where the activated complex is much lower than it was before. And so the activation energy is also lower. You lower the hurdle, lower the barrier, and more molecules are going to be able to react. This is going to lead to a faster rate. This is our catalyzed curve. Notice that with the catalyst, the reactants are in the same spot and the products are in the same spot. Only the activated complex and the activation energy are lower. You've lowered the barrier so that more molecules are able to react. Now let's look at the endothermic reaction. The setup of our graph is the same. Potential energy and reaction progress. Reactants and products. Notice that this time the reactants are lower and the products are higher because endo means energy in. Here's our baseline and our normal curve. To get from the reactants to the products, you have to go through the activated complex first. That means you have to have this much activation energy. This is our normal curve. If you add a catalyst, you change where the activated complex is on the energy scale. You change the amount of energy that is needed to make the reaction occur. And so more molecules now have the energy to jump that barrier. Notice that the reactants are the same and the products are the same. Only two things have changed. The activated complex has changed, and the amount of energy needed has changed. Last thing, it is possible to have something like a negative catalyst or a reverse catalyst or the opposite of a catalyst, and that's called an inhibitor. An inhibitor does the opposite of a catalyst, but it has one thing in common. The chemical itself is still not used up. But instead of making the rate go faster, it makes the rate go slower. And instead of lowering the potential energy barrier, it raises it. So your graph would look very much the same, reactants and products would be the same, but instead of lowering the hurdle, you would raise the hurdle in the middle. So you would again change the activated complex and the activation energy. Congratulations, you're done with reaction rates.